Hi class, in this recording we're going to focus on acids and bases and buffers, what they are. As we look at acids and bases and buffers, these are very important to our body in that they help us to maintain homeostasis. If you've forgotten, that's okay. Acids, generally speaking, and this is the Arrhenius definition, are something that is going to add a lot of hydrogen ions to solution, whereas a base is something that adds a lot of hydroxide ions to solution. This is really a good workable definition for this class. As we look at acids and bases and how they help us to maintain homeostasis, there are enzymes in our bodies that we use to regulate our chemical reactions that we need to stay alive. Our metabolic reactions, they're very sensitive to pH fluctuations. If we change the pH of solution, we are going to change how many hydrogen ions and or hydroxide ions are capable of binding to the functional groups or the side chains of the amino acids. So within an enzyme, we have an active site, and the active site of the enzyme is the part of the enzyme that actually accelerates the chemical reaction by reducing the activation energy needed to kickstart the reaction. And if we change the pH, the active site is going to change shape. So if I add too many hydroxide ions, if the solution becomes too basic, those hydroxide ions are then going to bond to the positively charged amino acid residues. And that will cause those positively charged amino acid residues to no longer chemically bind to the negatively charged amino acid residues. So over here, we can see the positive and negative residues interacting with each other so that the protein will have a specific shape. And by modifying the pH, we sever the bond between the positive and negative amino acid residues, causing the protein to change shape. And if we change the shape of the protein, we change the function of a protein. So a very slight deviation in pH can shut down an entire metabolic pathway by deactivating the enzymes that regulate those metabolic pathways. Now, as we look at the pH of a solution, a really kind of oversimplification is to say that P stands for power, H stands for hydrogen. It's the power of hydrogen ions. And I know it's different. It's the negative log base 10 of the hydronium ion concentration, but this is not a chemistry class. So we're just going to say the power of hydrogen ions. The more hydrogen ions you have, the more acidic it is. And if you add an acid to an aqueous solution, that acid will release the hydrogen ions and make that solution more acidic. On the flip side, as we remove hydrogen ions from solution, we are going to make that solution more basic. And then halfway between acidic and basic, where we have a pH of exactly 10, we have neutral. And there's one thing that's neutral, and that is going to be pure water. By definition, the only aqueous solution that is neutral is pure water. And we can have, just as a frame of reference, a lot of food products are going to be acids. The hydrochloric acid in our stomach is, well, an acid. It's hydrochloric acid, for crying out loud. Most cleaning products are going to be bases. So our body is really well prepared to handle the ingestion of acids. We ingest acids all the time. It's very normal. Ingesting bases, though, is something that we don't do very often. We have eggs, and I suppose if you eat blood pudding, that could be a basic food product, but ew, who eats blood pudding anymore? Ugh. Really, eggs are the only food product I can think of off the top of my head. Maybe lutefisk, but again, who eats lutefisk? Ugh. Most food products are going to be acids. Most cleaning products are going to be bases. And we can have strong acids. As we look at a strong acids are always, for the sake of simplicity, we'll say that strong acids give up nearly every single one of their hydrogen ions. So they have a very big effect on solution. Weak acids, though, only give up a couple of their hydrogen ions. So because they only give up a couple of their hydrogen ions, they don't have that big of an effect on pH. So carbonic acid, it's an acid, but it's a weak acid. It doesn't really acidify the solution that much compared to strong acids like hydrochloric acid or sulfuric or hydrofluoric or hydroidoic. As we look at bases, we can define a base as anything that accepts a hydrogen ion. Strong bases are almost always going to have a hydroxide ion associated with them. Sodium hydroxide, potassium hydroxide, magnesium hydroxide, calcium, so on and so forth. You get the idea. If there's the word hydroxide in the name of the chemical compound, you should think strong base. And that hydroxide ion with a -1 charge does a really good job of binding to a +1 hydrogen to make an H2O molecule. So when you neutralize a strong base with a strong acid, an acid-base neutralization will always give you a water molecule. And that should be reviewed from your chemistry prerequisites. Now when we look at weak bases like bicarbonate or hydrogen carbonate, that is not going to do a great job of removing hydrogen ions from solution. Just like a weak acid has a small effect on the pH of solution, a weak base also has a small effect on the pH of solution. So, and here's something that a lot of students struggle with. As you add more acid, the amount of acid increases, the pH decreases. And because that's kind of an opposite, to say if you add more of one, adding an acid lowers the pH, because we use opposite terms, adding versus lowering or adding versus subtracting, that can be kind of confusing for students. As we look at a base, the more base we add, the more we raise the pH of solution to make it more basic. Notice that pH goes, generally speaking, on a scale from 0 to 14, although for those of you who've had some fun with chemistry, yeah, it is possible to get a negative pH or a pH greater than 14, but oy vey, those things are scary. Don't touch. So let's talk about the human body. This is a human A&P class after all. Our blood has an optimum pH range of 7.35 to 7.45. So in other words, our blood is naturally alkaline, naturally basic, because the pH is naturally going to be above a pH of 7 or neutral. And as we look at our blood and its pH range, there are some things that are constantly trying to change the pH of our blood. We have some challenges that we need to overcome physiologically, such as our metabolism. The chemical reactions in our bodies are constantly making more acids and constantly trying to drive the pH of our body down. So let's think of lactic acids. When we have anaerobic fermentation and we are having to shift from the citric acid cycle to the lactic acid cycle, that's going to cause a lot of pH or acids to be dumped into our body to lower the pH. As we break down nucleic acids, so catabolism, thinking of digesting, chemically digesting, we release phosphoric acid. As we break down the triglycerides that make the fat, as we're burning our love handles off, we're going to release fatty acids into solution and ketone bodies, which help to acidify the solution. And if we hold our breath, we build up carbon dioxide in our bloodstream, and that carbon dioxide turns into carbonic acid. There are so many acids in our body. How on earth do we have a basic blood pH if we're constantly dumping acid into the blood? Well, we have some ways to help cope with that. First, we have a buffer. And a buffer, I remember when I was a freshman in college, this made my head want to explode. A buffer can be an acid and a base at the same time. It all depends on what you are exposing it to. If you take a buffer and you expose it to an acid, the buffer will act like a base and resist the change in pH. If you have a buffer and you expose it to a base, the buffer will act like an acid and resist the change in pH. All buffers do is they take a strong acid or a strong base and they make them behave like a weak acid and a weak base. And they make it so that the change in the pH of solution is going to be minimized. And we have lots of buffers in our body. These physiological buffers help us to modulate fluctuations in our pH. Otherwise, holding your breath would put you into respiratory acidosis in almost a heartbeat. Thankfully, we have these buffers. For example, our urinary system is going to buffer an incredibly large amount of acids and bases as we dump hydrogen ions or bicarbonate ions into our urine. You may recall from our discussion of the urinary system, we are constantly pumping hydrogen ions into our urine, and we're constantly urinating out, acid. Our urine is almost always going to be acidic, and that's how, at a very gross scale, we're able to compensate for the fact, let me back up here, go forward. That's how we're able to compensate for the fact that we're constantly dumping all these different acids into our bloodstream. Well, every time you go to the bathroom, or I should say nearly every time you go to the bathroom, you are going to urinate out a bunch of acid to help compensate for that. Now, the downside of the urinary system accounting for our acid buildup in our body is that it takes hours or days to have an effect. We're not constantly urinating every second of every day. So we need something that works fast. The urinary system is a good long-term solution, but we need a short-term solution as well. And our short-term solution is our respiratory system. And instead of taking hours or days, it takes minutes to modulate the pH of our body. The downside is that this respiratory system, the rate of inhalation and exhalation, our respiratory rhythm, can't have that very big of an effect. We have a little bit of an effect on pH with our respiratory system, but it's really hard to match the urinary system's overall effect on our pH. So we have a very quick and weak response with our respiratory system, and we have a very slow and strong response with our urinary system in terms of controlling and buffering and modulating our overall body's pH. Now, as we look at our body, we have more than just physiological buffers. We have more than just the urinary and respiratory system. We also have chemical buffers. We have substances in our body, in our blood, that can attach to hydrogen ions and remove them from solution, or release hydrogen ions into solution if we are having a fluctuation in pH. And these chemical buffers are near instantaneous. They work over the course of seconds. And if you've taken a general chemistry class, this is the classic chemical buffering system that you talked about in those classes. These buffering systems are going to have a weak acid and a weak base. So here's our acid, our weak base, and they're going to be combined together to allow for us to neutralize a strong acid or a strong base. And we have three primary chemical buffering systems within our bodies. We will not be talking about them in this recording. Our next recording will be focusing on those. Those primary buffering systems, the bicarbonate, the phosphate, and the protein buffering systems within our bodies to help us control fluctuations to our body's pH from a second to second basis. Now, as we look at these buffering systems, the amount of acid or base that they can neutralize typically is going to depend on how much buffer we have. If we have a high concentration of buffer, they can neutralize more acid or base versus a low concentration of buffer. And it also depends on the pH of the working environment. If we already have a very alkaline pH to start out with, the buffer isn't going to be able to neutralize that much more base because it's already in that very alkaline environment. So, that's all we have for this recording. If you have questions or comments about acids, bases, and buffers, please feel free to post them in the class discussion board or to shoot me an email. And as always, happy studies.